Greetings, felicitations, welcome to another video. So in the background there you can hear I'm reprinting this thing, and that's because it's here it's broken up into two parts, and that's an artifact of when I was going to have it as the bottom of a sort of a two-layer rotor, but right now it's got a little bit of wobble. It's not terrible, but it's just sort of, I can get rid of this and make it one piece, and the more consistent I can make things, the better. So I need to print that, and then from what was seen in the last video, I need some new coil forms. One like this, but the height of this one. And that was all covered in the last video, so I'm not going to go over that. But while this stuff is printing, and then I need to wind the coils, there's still some things we can get to the bottom of with this. And one question that should be simple and straightforward, and I'm pretty sure I know the answer to this, but we're just going to confirm. And that is, whenever, where do I begin? To give the grandiose 30 million mile view. Whenever there's a change in the rate of flow of current, something mysterious happens and another current appears. It can be called an inductive spike, it can be called a displacement current, it can be called a radiant spike, whatever you want to call it. Whenever there's acceleration or deceleration of current, you get this current that shows up. So when you have something like this, which is called a pulse motor, you just briefly pulse this coil. And so the current in here is accelerating and decelerating all over the place. And you can capture that. So let's say later on I'll put it together, but we have that there. You have a current that's showing up because of the change in the magnetic flux in this coil, to sound a little more formal. Now you also have the magnet spinning past, and this is a coil of wire, so that comes into play too. But you have this. Now let's try and think about this slowly and just forget about the spinning rotor for a minute and just consider pulsing the coil. So you pulse the coil and the amp flow is increasing. Then you shut it off and it goes back the other way. So there are actually two places where you could try to look to gather energy. The first is when the coil is charging up, and the second is when it's collapsing. Now, I don't know an easy way to capture it when it's charging up, because you end up shorting the thing. Maybe at some point I'll go into that, and maybe at some point maybe I'll figure out a way to solve that. So you forget about that one. Now, all this, when you pulse it, it's going to happen in 1/100th of a second or quicker, but let's just be silly and say like it's a 10-second pulse. So for 10 seconds this is increasing in current, and then but there's nothing you can do with that changing magnetic flux. But then when it collapses, the current that's being produced, the inductive spike, is of opposite polarity than what you're putting in. So you can grab that, and you need to what's called rectify it. So how would you rectify it? Now that's where a diode comes in. Now a diode, I guess the best analogy, I'm not a plumber, so I don't know if I have the terminology right, but I think it's called a flapper valve, where water can flow through a pipe one way, but then if water flows back, it flaps shut and stops it. So that's what a diode does for electricity. And if I can scroll down here you have the symbol for a diode. So what this tells you is that you can go from positive to negative that way, and there is not a lot of resistance. There's a voltage drop, but once you get past for a silicon rectifying voltage, you're going to need like 0.5 to 0.6 volts, and then it opens the floodgates. And now it will pass through there with resistance almost like a straight line wire. But it can't flow back this way. So what that means is if you put a backwards diode on this thing when you pulse it, when that backwards energy, that backwards current comes through, it will flow out, but then it can't flow the other way. So you can put it into a cap or into a battery or something like that. So that's the first way. That's called single diode rectification. Now there's a second way to do it, and it's called a full wave rectifier, and we'll talk about why it's called a full wave rectifier in a minute. Here on Electronics Tutorials is a picture of a full wave bridge rectifier. And so this is a alternating current source. So let's look at this thing in a little more depth. Since it's alternating current, sometimes this will be positive, sometimes it'll be negative, and vice versa. So let's say you have a positive coming in here. Now it sees two diodes. This one is blocked. Remember what we just talked about. But this one, it can flow from positive to negative. So it flows out, boom, 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 boom. Gets to there. Now it sees a blocking diode. Can't get back to there. So that's clever. So it's stuck there. Now the negative, we said that was the positive. The negative goes around here. Now the negative can flow through here. You know, it's going this direction, and it does the opposite of the positive. So it can flow through here. It can't flow through there, so it can't get to there. Now it gets out to here, but it's an opposite diode. It's trapped there. It's very clever. So why would you want to use a full wave bridge rectifier instead of single diode rectification? And to understand when you want to use full wave or single diode rectification, I need to throw one more wrinkle at you. And that is that this is currently set up as what's called a monopole pulse motor. So that means this magnet's facing north toward the ceiling, north, north, north. Now you put your coil here and you pulse it. Let's say it's, you know, in repulsion, so it, you know, is there and it pushes the magnet away. And then you want to push the next magnet away. So you put the same polarity of current into the coil. And then you do it again, the same polarity of current into the coil, and again and again. And, you know, here's my incredible graphing skills. So just to be kind of, you know, make it a little graphical, the current is going like this. The yellow line is 0. Boom, back to 0, boom, back to 0. So in this case, there's not really any need to use a full wave bridge rectifier because you're not putting alternating current into the coil. Now, I mean, this is just a little distinction. You know, when the coil rings, it alternates. But I'm talking about what you're pulsing into here. You're always pulsing in the same polarity, and it's going like that. Now, again, that's different from the ringing of the coil, but we'll leave that one alone right now. So you would want to use single diode rectification because, well, let's do that one. So let's say instead you have, instead of a monopole machine, you have a bipole machine. That means that this magnet's facing north towards the ceiling, and this one's facing south, and this one's facing north, and this one's facing south. Now, one of the nice things when you do that is if you put a coil here, depending on the spacing of the magnets, you'll be pushing, say, this magnet out, and you'll be pulling this one in at the same time. So you get a push-pull, and that gives you a little more torque and a little more efficiency than a monopole setup. But now, first it sees a north-facing magnet, and then it sees a south-facing magnet. So if it pushes this one out, and you put the same current in with the south, then it'll pull that one in. So all it'll do is go boom, 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 and you won't get anywhere. So what you need to do is reverse the polarity each time, so that this is north and then south and then north and then south and vice versa down there. And so you switch the polarity. Now what you'll see, again, I apologize about the graphics. This is your zero line. The current will go up, go back to zero, but now the next time it goes below zero and then back. So if you only had a single diode, the first thing is that you wouldn't be able to rectify half of it. You would only be able to rectify this part, but this part's the wrong voltage for it to be able to rectify it with a single diode. Now the second thing, and I'm not going to confirm this today. When we start running this as a bipolar machine, I'll confirm it. But it seems pretty clear also, if you just have a single diode, this is going to be a dead short. So that's not going to help you. It's not only not going to rectify, remember that it just needs 0.6 volts to start flowing with next to no resistance. And so here it's in a blocking configuration, capturing that backwards spike. Here the thing's already backwards, and it can flow right through the diode. So, oh no, what do you do now? So now you go back to that clever, I don't know who invented it. Maybe someone will teach me. The clever setup here of the 4 diodes, where now you can have it boom, 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 and it's always, these two are always isolated by diodes. So when you go to a bipolar machine, you want to use a full wave bridge rectifier. When you go to a monopole, you can use either. But if you have a monopole setup, you know, is one of them going to be preferable to use? And the answer is yes. Now recall, there's a 0.6 voltage drop across a diode, right? Now in these experiments, I'm running at 4 volts. So 0.6 is actually a fair amount. Now, if you have a single diode, which you can get away with here, you only lose 0.6 volts. And, you know, if you're running at 60 volts, it's much less of an issue. But at 4 volts, you know, it's a pretty significant drop. There's only 3.4 volts making it to the coil. But if you have a full wave bridge rectifier, this one goes through a diode, and this one goes through a diode. So now, instead of a 0.6 voltage drop, you have a 1.2 voltage drop. So again, running at 60 volts or 120 volts is sort of like, who cares? They're basically the same. Running at 4 volts, you know, instead of losing 15%, you're losing 30% of your voltage to the coil. So let's just talk through this circuit for a brief moment. And you have your Hall effect sensor, which is telling you whether it sees a magnet near it. If it sees a magnet near it, it tells switch 13 to close this switch. When that switch closes, power flows from the positive here through the red line across the switch to one end of your coil, around the coil to the ground, which is where this black one is. So if I connect the black line to there, the thing should spin. Now what else do we see? We see a backwards diode. See, this is the positive, but you can see there is the line. So that blocks current flowing there. And then the other end of your cap is out to the negative bus line. So again, when the coil collapses now, reverse energy, opposite polarity electricity, can now flow through here and end up in the cap. And you know, one funny thing is this is the negative bus line, but this becomes the positive of the cap, and the negative of the cap's over there. And so that's how you capture it. Now, what do we have over here? Does that look familiar? It should. That's a bridge, a full wave bridge rectifier. And it's not doing anything right now. Later on we'll hook it up. But first we'll do the single diode. Now, you can look at it without a resistor across the cap, or we can put a resistor across the cap. And what I've done is I've looked at different resistances, and I'll try and touch on that very briefly. And in fact, one of the things that'll be fun is we can just put a dead short across here. And we'll see what happens with the motor then. And we'll talk real briefly about why that is. So I don't know what this is. Let's put in a 1K ohm, and then we'll look at the spike, and we'll see what we get. Okay, so we got the battery there, we got the Arduino plugged in. I put a meter across here. We don't have any resistance across there now, so when I connect this to here, it should spin. There we go. Everything's coming up Millhouse. All right, so let's put an amp meter on there once it's spun up, just to take a look at the amp draw, and we'll see what it does. You know, we're getting 74.7 volts into here from 4 volts, which is kind of cool. And then we're also going to look at it with 1K and maybe 100K, and then we'll move over and do the same thing on the full Wave Bridge Rectifier, just so you can see that it's no different, but just a little bit worse. Okay, we have the thing spinning now. We got 75.3 on the cap, and we're drawing, I'll call it 55 milliamps. And we're spinning at 829. It's still climbing a little. I'm going to give it a minute to settle out. Okay, I've let it spin up, and I think we're at, it was 824, 823. It was at 824. We're right around there. Maybe the battery's going down a little. 50. I was calling it 52. It looks more like 55 now. 55 and 76. I mean, I'm jotting this down. It's getting too crowded to type. It's changing a little bit. I'm going to jot that in, and then we'll put in a 1K. So I put in a 1K across the cap that's gathering the spike. 831 and climbing, whereas we were at 824 before. I don't understand that one. We'll just call it like 832. Oh, I'll check it in a moment. The milliamp draw. Yeah, it's the same, right at 55 again. And the spike voltage is 1.97. Let me just check the RPMs one more time. Go to 10K, then we'll go to the full Wave Bridge Rectifier. I'll call it, yeah, I was saying 832. It looks like that's about where it is. So 824 to 832 with the load on it. I don't know why. So 100K, 37.8 volts, again 55 milliamps, 827 instead of 824. And last thing before we go to the full wave is we can put a dead short across the cap. Now, I'm not shorting the coil. Okay, if you short the coil, this thing, I'm pretty sure it's just going to come to a stop. I mean, I did a little of that, but I mean, then you just have a dead short across this line, and nothing's going to flow into the coil because all it has to do is flow through your little alligator lead. But if you put it across the cap, you still have the isolation from there. And just to show what happens there, let me get the two leads from the cap. So just plain old shorting the cap right now. Yeah, and of course that goes to 0, but yeah, 55 milliamps. That's kind of cool. Let's look at the rotational speed. Okay, so it is slowing down, but it'll still keep spinning. I mean, it'll probably go down to about 600. Let me do this. Okay, see, it's climbing from 589. So that's kind of neat. Now again, you're not shorting the coil. You're shorting the cap that's gathering the inductive spike. But it's kind of neat that you can get away with that. So let's move over to the full wave bridge rectifier and finish this up. Okay, so now we have the inductive spike being rectified by a full wave bridge rectifier. These two lines should both be orange or something. This is just what I had lying around. But the positive and the negative are where the cap is. The spike is 75 volts, 75.1 versus it was 76 before. Rotational speed's about the same. I'm not going to bore you with the 1K and the 10K through here. What it boils down to is that it's pretty much the exact same. It's just a little bit worse with full wave bridge rectifier because you're going through 2 diodes instead of 1. Let's just do one last thing with full wave bridge rectifier, which is to short it, and that's to show that, yeah, even though you got those 4 diodes, there's isolation all around. So if I that was just a cap discharge. If I short it, amp draw's gone up. I don't recall that happening before. I'm gonna do it off camera once more with the single diode. Because with single diode, I don't recall the amp draw going up. So the amp draw has doubled. Let's see if it keeps spinning or not. Yeah, it's still spinning. So I mean, you need that isolation from the diodes. I don't know why the amp draw did double. I guess just there's more places for current to leak. I'm going to do it off camera once more with the single diode just to confirm that the amp draw didn't go up. But that's cool. That you can just flat out short the thing. And if you're using a resistive load, a reasonable one like 1K, 100 ohm, 10K, it behaves pretty much the same as a single diode. It's just more complicated, and you have a little bit more loss through a second diode. Last thing, and then we'll wrap this up. Well, I mean, I've shorted across a single diode again, and yeah, I mean, maybe we're up to, it's not focusing. Focus. I think we're up to like 60 milliamps or something. But it didn't double, like with full wave bridge rectifier, so I didn't see that one coming. I don't know exactly what's going on there, and I don't care. It's just, if you use a monopole, use a single diode rectification. If you're using bipolar, you need the full wave bridge rectifier both to catch the negative, and also the single diode would just be a short on half of your cycle. So we can, confirm that, show that when we go to bipolar. But last thing in a spreadsheet, let's put this in a spreadsheet. This is kind of interesting. Okay, let me just do this again and see if maybe I did the math wrong the first time. So we had a 1K, this is with the monopole single diode rectification, 1K across the gather cap, and the spike went down to 1.97 volts. 100K, it was at 37.8, and with no resistor across there, it was like 75 or something like that. In all cases, we had the same battery. It was right around 4.1 volts, and we saw the milliamps didn't change. It was right around 55, 52, right around there. So we can ignore all that. The input's the same. So if I'm doing this right, maybe I'm doing something stupid, but Ohm's law, V equals IR, therefore I equals V divided by R. We know V, we know R, so we can figure out what the milliamps into the cap are. So in the first case, it'll be 1.97 divided by 1K, which is 1,000. In the second case, it's going to be 37.8, equals 37.8 divided by 1K. Come on. 100,000. Okay, so far so good, sort of, because here, well, that's amps. We got to times it by 1,000 to get milliamps. Equals this times 1,000. I'm sorry, yeah, milliamps. So just about 2 milliamps there, 0.4 milliamps there, which on the surface seems okay. We put in more resistance and your amp flow, as you would expect, decreased. However, we put in 100 times more resistance. So why isn't it 1/100th? And if we talk about power out, which is milliwatts, then that's going to be equal to voltage. Now these numbers match 1.97, 1.97 because it's multiples of 10, 1K, 100K. If it was a 2.2K ohm resistor, they wouldn't match. But so you have 1.97 milliamps times 1.97 volts equals boom times boom. You're putting out a cool let's round it up to 3.9 milliwatts. And with the 100K, we got boom times boom. You're putting out 4 times more. Just about 4 times more milliwatts. 4 times more power with 100K versus 1K. That makes no sense to me. But, you know, it's neither here nor there. I just filing it away is another thing that I don't really get with pulse motors, but it's kind of cool. So if you can believe it, my goal was for a 5-minute video. That's shot to hell. But in any event, thanks for coming along. Gotta print some stuff now, print that, and then, as I said, print the new coil forms, and then back at it. It's actually coming together. I know it doesn't seem like it, but it is. And this is a finding I don't understand. I'm just filing that one in the back of my mind and let it percolate. And you know, you do that, and sometimes it's like months later. It's like, oh wow, you know, that relates to that. You get an insight. Okay, sorry. Thanks for coming along, everyone. Don't forget, if you want to like, subscribe, and comment. It's always nice. And stay healthy, and until next time, ciao. Bye-bye.